Hello everyone, it's May the 18th. I'm gonna do an early one today. Let's see. I always want to know if it's really like, late at night, the brain gets fuzzy and then the performance starts to drop. And early in the day, it's kind of, everything is fresh and I just took a shower. So I hope this actually helps. All right, let's take a look. Find duplicate file in the system. Interesting. Oh, so we're gonna parse this. Now, of course, I think we can use a library to do this, but let's not go that route. So, given the list of paths, including the directory path, and all the files with contents in this directory, return all the duplicate files in the file system in terms of their paths. You may return the answer in any order. A group of duplicate files consists of at least two files that have the same content. A single directory in info string in the input list that has the following format. So root / blah 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 DM. Oh, we have content as well. Oh wow. Oh, it could be different files. Oh, we want to find. Hold on. What are we trying to find? All the files with content. So we have content as well. Return all the duplicate. I thought just return the duplicate files. In terms of their paths, you may return. Okay, it means there are n files, f1, f2 to fn, with content f1, f2 to fn, respectively, in the directory this. Note that n is larger or equal to 1 and m is larger or equal to 0. If m equal to 0, it means the directory is just a root directory. The output is a list of groups of duplicate file paths. For each group, it contains all the file paths of the file that have the same content. A file path is a string that has the following format. So it's not exactly the same. So they have their own way of defining the trajectory, the directory, and then the content. Okay, so single directory info string. This means I have these files. Again, what are we trying to find? All the duplicate files in the file system. Oh, we're trying to find from different directory. Like, okay, so we have root to folder A. We have 1.txt. And these are all numbers, right? Because f1, f2, f1.txt, f2.txt, and f1, f2. I don't know. Is that f1 f2 is always 1.txt, 2.txt? It doesn't really matter. So of ABCD, EFGH, ABCD, EFGH, EFGH. So we want to group them together. Root A 2.txt, root C D 4.txt, and root 4.txt. Yeah, and then root A 1.txt and root C 3.txt. Ah, okay. Okay, I see what this is. ABCD, EFGH. Okay. We have 2 times 10 to the 4th on paths. Paths, okay? And each path I, that's a string, right? String length is no longer than 3000. Sum of all the paths, okay, consists of English letters, / dot, parentheses, and then it means white space as well. You may assume no files or directories share the same name in the same directory. No files directory share the same name in the same directory. So within the directory, there will be different names. You may assume each given directory info, this, right, represent a unique directory. A single blank space separates the directory path, is the path, and file info. Follow up. Imagine given a real file system, how will you search files? DFS of the how would you search files? File content is very large. How would you modify a solution? If you can only read the files by 1 kilobyte each time, how would you modify a solution? What is the time complexity of your modified solution? What is the most time-consuming part, the memory-consuming part? How to optimize? How to make sure the duplicate files you find are not false positives? Oh my God, this is okay. Let's don't worry about that follow-up. Let's just solve this problem first. I mean, we're given path, right? So each path we can break it down. So we have the directory and we have each file names, right? So we have that. We can say the directory is going to be a no, the content. Oh, that's what we're gonna do, right? We're gonna say the content. We can do a content as a key. I mean, because the content, oh, actually, I'm not sure how large the content is. I mean, it says file paths the length, so at most is 3,000. So it's going to be a 3,000 at most, right? The key could be 3,000 in length, which is fine, right? We can handle it. So we use the content as key, and we put all the files that has the content into a list, and then we return the list of it. Okay, so that's how we're gonna solve this problem. We're gonna think about how to solve the follow-up problem later on. Follow-up problem, and yeah, it's gonna pose an issue. I can already see that, because if you have like a lot, right? It's a lot, and then it's hard to. And this is BFS. If you think about it, we go through each path, right? We go through each path and we try to find out everything. Is that BFS? No, it's actually DFS, because you go down to the level of files. You go down to the level of files. That's what we do to the files, and then get the content, and then you use a mapping between content and the directory. So that is BFS, which I think might be the one that take the most of the time. But anyway, we're gonna say, what do we say? We say content map, right? So we're gonna have a content map. Let's call it from collections import default dict. So content map, we can go with default dict list, and then we're gonna say for path in paths, right? So we have each path coming in, and then we're gonna say plist equals path dot split. I think we can split on empty. So the first one will be the root. The second, continue on, will be the files. So within the files, we can also look for the content contained within the parentheses, which I think we shall use regex. It will be easier to handle this. So we're going to import regex, and I don't know, every time the regex have to test on regex, because I forgot. Let's say a1.txt. So what we want is, I mean, we can do this without regex, but I think regex will be the easiest solution to get this thing out. So that's that, and we say re.match, right? We can say .match, and the first one is pattern. So the pattern will be anything, right? And then that's going to be in a group. And then we're going to match the left parentheses. And another group will be anything, but I actually don't know. It might contain nothing. hold on, let's see if we contain nothing. So directory n larger to, note that n is larger or equal to 1, so f1, but it didn't say like the content. I think the content probably could be empty. So it's content could be empty. Yeah, we have to take that into consideration, which means file name. File name. File name, I don't think file name is going to be empty. Note that n larger equal to 1. Yeah, n files. So we have files, right? We have files. So file name is not going to be, but content, I'm not sure. And we match our right parentheses. Right? So that's the pattern. String is going to be A. And we match. How do we get the groups? I forgot. Does that have to say match all, right? It's like, I don't know like how many times I've done this. Many times. Every time I need to do regex, I have to go through the documentation. Match just gives you a full match, split, find all. A list of groups. Oh, I think that's going to be find all. We want a list of groups. Hold on. Group. Pattern dot groups. Match dot group. Oh, maybe there's match dot group. Yeah, it is. Let's do this. M equals this. M dot group. Right. Group 0, the entire thing. Group 1, yeah. Group 2, that's it. So we expect to have, 2 groups. Okay, that's fine. So we're gonna split first, right? And then after split, we're gonna say for file and for file content in plist 1, because the 0 is the directory. So for each one of them will be basically this thing, right? 1.txt. And now we say m equals read.match. Actually, we're gonna copy and paste the regex we just wrote. Oh, I forgot that this cannot copy. I have to exit in order to copy. Doesn't support. So this and file content, right? It will match every single one. Maybe we should check it still. Yeah, FM. Yeah, let's check it. Then we say, like, if we match, then group 1. No, group 2 is the content. So we say content map, content map m.group 2 dot append. Append what? Append plst 0, right? Then we're gonna say plus a slash, then plus m.group 1, right? Because the 0 will be this part, and then the plus a slash, and then plus the content. Okay, so that's that. So we go through the entire thing, put them in, and then we're going to return list content map dot item, not values, right? Not values, and we are good to go, I think. I am going to test it, although it will be interesting to test, I think. So this is going to be the input, right? Input, oh my god, look at this. And this is going to be the output. How are we going to sort, right? It's how are you going to sort? We're gonna sort. I don't know. I don't know how you're gonna sort, but apparently you can, I guess. But otherwise, how are we gonna test? Like to say the two things are the same, right? I don't know. So this is gonna be the second input, and we also have the second output. Group them together. Okay. Now we're gonna handle all of these. They're gonna be single quote, and all the right, and all of this, and this. Okay, so this is going to be paths, and this is going to be find duplicate paths. Yeah, it's gonna say fail. So let's say we'll use sorted res equals to sorted answer. Will this give us a better? It give us a better result. So I think this is correct. In order to handle this, when might time out? I don't know. Try it. Give it a shot. See if it time out. Pending, judging. It'll have a wrong answer. What the hell happened to me? It has been this way for so many from yesterday. It's kept having wrong answers. The hell? Yeah, I want to see. Like, what could be the situation? I didn't know. Let's try it ourselves to find very unfortunate. I have this. All right. I don't know, man. It seems right to me. Let's use this one. Easier. So what if we have no content? Right? Is that the thing that we're talking about? Like if we have no content, what's gonna happen? Your answer, expected answer is still okay, it's still correct. No answer is correct. What if we do this? Oh, my answer and expected answer. Oh, duplicates. All the duplicate files. Oh my god. This one's not duplicated, so you don't include that. Aye. Alright, this is my fault. So that is going to be a list comprehension then. Which just means value for v in this if len v. Right? Then this one shall be good. No. Len v is larger than 1. Len v is larger than 1 because we want duplicate files. There we go. All right, let's give this a shot. Pending, judging, accepted. So this solution works simply because we have only 3,000, right? The length is only 3,000, so that makes it work. What's about the runtime? Runtime will be anyway. So since the content size is quite limited, at not longer than 3,000, we can directly use the content as a key for a content file mapping. We loop through all the files in the path and place each file directory into a list corresponding to the content, and this allows us to group all the files that have the same content together. The one tricky part is in the return. We only return the files that are duplicates. And the runtime, so we go through path, that's on, right? And when we split the path, that is going to be, let's say, OL. So ON times OL. I mean, what do you consider on the rejects? Like if we ignore the runtime on rejects, we have O n, let's call n m, where n is the size of paths and m is the number of files within each path. And we run this at 104 milliseconds, or 26% ranking. Okay, so now we need to go back to the problem, trying to think about, do I have a solution for this? Yes, we do. Think about the follow-up. A real file system, right? So search the file DFS. Of course DFS, because BFS you need to keep everything in a queue, which is gonna grow. Well, this you have to keep it in the. This you have to keep in the stack as well. But I think DFS, the size of the stack will be smaller than the size of the queue, because BFS, you don't know, the file system can be tremendous, gigantic, right? So it just spreads out a lot, but the depth of the file system most likely is limited. We go like regular file system, I think the deepest you go, you won't go like 100 level deep, but you definitely can have more than 100 files, 100 folders. So the BFS will take up lots of memory. So definitely we're going to go DFS to go to each files, put each folder and go to the files. Now the second question, if the file content is very large, how will you modify a solution? Well, of course, if the file content is giant, we cannot do this, right? We cannot just grab the content and make that into a key. But what we can do, right? What we can do is just, what we need is turn a giant file into a unique string, right? And I think in cryptography this is possible. We just pass this giant blob into some algorithm, and then that algorithm will reduce that into a smaller string, a small, like say, a 128-bit string, and then that will be the representation. That will be the signature, right? That will be the signature of this file. And I think it's possible to do this. So we just may basically convert a file into a unique, for each file into a unique signature, and then we use the signature as the key for the content map. So that's how I would solve it. But like how fast it is to convert a gigabyte level file into a signature, I don't know. I have no idea. But I believe it's possible. All right, let's just say that's the solution. Go on. If you can only read the file by 1 kilobyte per each time, how we modify. So now we cannot read the entire gigabyte level. So we can only do 1 kilobyte at a time, 1 KB at a time. So we just read the first KB, right? We read the first KB and then we save the files that, depending on the first KB. If the first KB is different, then it's already different. It's going to be a different file. So we group the files together based on the first kilobyte of the content. And we get rid of all the unique ones, right? The one that doesn't fit. Now within the ones that does fit, then we just keep reading. And we just, as we know, it's 1 KB, right? So we're just starting from 1 KB to read another KB, right? So just progressively, we group together the files that's the same for the first KB, and then within those files, we try to find the files that's also the same for the second KB and the third KB, and then we kind of just sieve out anything that's not belonging to this group, and they will form their own group, right? So with each time we run this, we'll get a group, we'll get groups, and then within these groups, we'll get subgroups. And it's actually possible every time we get subgroups, and we also flatten them out, right? So we just keep going until we finish reading all the files, right? So that will be my solution for this for the third question. What is your time complexity for your modified? Well, the time complexity for so we have to go DFS to find all the files. So that depends on that's going to be like O n. N is the total number of files. And once we find the files and then we make the grouping, we go through each file first. The first round, we go through each file. That's O n, right? Let's say n is the total number of files. We go through each file, that's O n. And in the second round, within each subgrouping, we have to process the files again, right? Have to process the files again. Let's say the worst case scenario, nothing gets thrown out. So every time you have to process O n, right? And then every level is O n. That's true. And then we will end on the size of the file, like how many times you need to read a file. So let's say on average you need to read a file m times, so the total runtime will be O n m. What is the most time-consuming part? Well, the most time-consuming part is we have to repeat the same process over and over again. That's the most time-consuming part. Memory-consuming part is to maintain all the files, right? To maintain all the files inside a mapping, right? We have to keep all the files in it, and we need to also, every time we rerun it, it's going to be a new mapping. So that's also time-consuming, memory-consuming. How to optimize? Well, one way to optimize that I can think of is after the first run, and we break it into subgroups, right? And then when we break into subgroups, different groups after the first level of grouping, they no longer have anything to do with each other. So we might be able to do, let's say we might be able to do multiprocessing, right? Threading or whatever. So because each one can be processed by itself, we don't have to group them together. So every time we break it open, we just throw them different threads. So that can help with the runtime. So we do parallel on that. And also that helps on the memory as well, because we don't hold the entire files. So every level down, right? We only hold the group, and the group will be smaller than the entire thing. So as we break it down and down, it will become more and more memory efficient as well. So it'll be time efficient and memory efficient. Yeah, that's how I would do that. How to make sure the duplicate files you find are not false positives. So we just have to read the entire file, right? You have to read the entire file. But that will be time consuming, I see, right? If you have a gigantic number of files. I mean, a random sampling? Is that what we think? Like, if we say we don't want to read the entire content of the file, we only read, say, 10 kilobytes, so 10 times, right? And we say like we read, like say we read 50%, right? We read 50% of the file, or maybe even less, right? We can do random read. I don't know if it's possible, but we can read so we have a file size, right? File size, that's something to check as well. If two files have different size and they are not the same. So we take the file size first, right? That actually should be the first. The file size. And, oh, hold on. But It depends on, yeah, I think it's fine. The content, the file content size. The file content size could be the first differentiator, right? And we group the files with the same size together, and then we can do like random reading, right? Random reading. We say 1 kilobytes. We don't read from the start. We just say, okay, now we're gonna read, say, 20% into the file. So everybody gonna start reading 20% of the file, and then we take 1 kilobyte out, and then we start grouping, right? And then after the group, we obtain a group, we take another, like another random place. So we do it a couple of times, and then, so we don't have to read the entire file, just do it a couple of times, and then we have our grouping. Not false. I think by doing this, it can reduce the false positive, because every time the 1 kilobyte chunk we read is going to be random, right? A random chunk of the file. So, and we can calculate the probability, right? If we say we do 10, if we do 10 readings and 1 kilobyte, let's say the entire thing is going to be a gigabyte. Each file is 1 gigabyte. So 1 kilobyte is 0.001. No. 1 KB is 1 over 10 to the 6. Right? 1 over 10 to the 6. So if we read 1 kilobyte of file, let's say we read it 10 times, right? Randomly 10 times. So that's 1 over 10 to the 6 to the 6th power. And if the probability that if all of them are the same, right? If all of the 10 times reading are all the same, then the likelihood that these two files are actually different has a very low probability, right? So like, because it will be each time the likelihood there will be not the same. I mean, hold on, the probability that they're the same if we read one chunk and they're the same, right? And then we read another chunk and they're the same. So the probability that the two files are identical, the probability will be like, all these chunks are the same, but the rest are not the same, right? Will be, yeah, will be very low. So I think that's how we can avoid false positive. All right, that's my analysis. Let's look at the solution and learn something new. This might be, I think it's a medium question. Yep, it's a medium question. Brute force. I brute force it. How's me not hash map? That's the one I use. N times X. I got this one correct. You'll get skill at reading the description. It's not even close to a medium question. Yeah, I agree. So it's just reading, right? Yeah, the follow-up. It'll probably be, oh God, this is probably just be the most simple thing you have to solve, and then we'll focus on the follow-up to build upon it. It's a simple hash map. Sorry that string 1 is the same as string 2. But depend with a good hash, right? All right, what's the brute force? File names and the content separated by, then what? Full path of every file along with the content of the file. And then you compare the contents. No, nobody will do that. Nobody will do that. Hash map. Let's see if I don't want to read. Let's just see if the key value. Yeah, it's the same idea. Yeah, it's the same idea. All right, I think somebody, does he give some insight? This means the files are located close to each other are also accessible. Locality is great for space locality, and that's why BFS got to be faster. Also, easier to parallelize. Oh, I say BFS is faster. Hold on. BFS explores neighbors first. This means that files which are located close to each other are also accessed to one after another. Okay, so I was thinking you have gigantic number of files. How can you do it? Like, how can you handle a gigantic number of files? But you don't have to. You don't have to put them in a queue. You just visit them one by one. You can do like lazy evaluation. And you have a higher chance of them if you're finding the same, right? So great for space locality, and that's why we expect to be faster. Easier to parallelize. Parallelize. My thinking is completely wrong. DFS will require a lock on the root node. But BFS doesn't require a lock. I still don't like. How do you get to the file? If I visit neighbors, right? I have my folder, and my neighbor folder. A neighbor folder, and I push in. And I go this folder, neighbor, next folder, neighbor. You have to put it in the. No, you still need to put that in the queue. How do you handle if I have like 100 folders and each folder is like one level deep? How is BFS? I mean, the runtime is the same, but how is BFS better in terms of space complexity? All right, very large. Compare size. Yeah. Oh, it's called hash. I was talking about cryptography. It's called hash. So with a hash, compare byte by byte to avoid false positive due to collisions. Remote file system. L is the size of the maximum bytes that need to be compared. All files are hashed and inserted in the hash map. And L is a file name. I don't understand on the BFS versus DFS. Principle for locality. So similar data close to each other in memory to take advantage of temporal and spatial is not organized in this manner, then it might be sent to use DFS. Keys group them in the map. Continue to hash the rest to further separate. Compare them byte by byte. Yeah, that's what I think, right? Tool Army. Okay, so who wrote this? Tool Army wrote this. So gigabytes digest algorithm and collision check will help. Now we're talking about their physical memory space. It's the entire directory, and this could be a problem for other write operation. How is it easier to parallelize? And that lock will be active for a longer time. There are a lot of nodes, and there won't be. I think there won't be a lot of nodes under X, because there's only so deep we can go. It won't be like too deep, but you'll have a lot of files. But they're in the queue. If they're in the queue, then they don't have the lock on. I think that's what it means. Right? If I have tons of folders in the queue, but they're waiting to be executed. So during the time they're waiting, you don't need to have a lock on them. You only need a lock on the one that's currently being executed. That's why. Oh, I know. I see the point of BFS being easier to parallelize, because for all those folders, you can throw each folder into a thread, and that's fine, right? You can throw each folder into a thread. DFS is, yeah, you cannot throw it because it's related, right? You're going deeper. Your parents are related to you, so you cannot throw the children just to a thread. That makes sense. Okay. Queue size will grow exponentially. That's my thing, right? It's the queue size. How would you deal with that? Store the queue on a disk. Comment the result of two different hash. Much better. But we don't care about collision-proof hashing. We could just pick the fastest hashing to begin with the result hash code in comparison with user time. Yeah. I just explained why using multiple hash isn't necessarily better than one to avoid collision. If we want to make two shots, yeah, it has to be byte by byte. Principle of locality. Okay, take a look at principle locality. And look at other people's answers to follow up. Can take advantage of the locality of files, therefore will be faster. If the file content is very large, not hash, it's not practical, you use files according to size. Yes, files with different sizes are guaranteed to be different. Or then hash a small part of the files with equal size. Yes, only if this is the same, we'll compare the files byte by byte. Okay. We can create a hash from one, yeah, and then read the entire file if a full byte by byte comparison is required. The worst case, when you need to compare every file to every others, K is the file size. Okay, yeah. How to make sure duplicate files. File size, hash, and byte by byte comparisons. Well, I think it covers everything. MD5 and SHA-256. Yeah, byte by byte is going to be time consuming, and the hash probably is too. All right, I have some more reading, but that will be it. It's a good question. It's a good question. Actually, I want to read this, so I'm gonna put that in a separate window. So I'm gonna read it. I don't think that's the one. I think I have two references. Let's take a look at these. Submission. I think I just, yeah, that's the only question I've done. I haven't done it before. All right, that's it. That's it. Good question. Good question. I'll end it right now and see you guys tomorrow. Adios.